Hey, Taylor, can you hear me?
Yeah,
Taylor?
I can hear you. Yep. All right.
So is this the same ID? Okay, looks like it is a different ID. 293398.
Yeah, I don't know. For some reason on the calendar there were multiple versions of it. I'm not sure how that happened. Um, anyway, so this is streaming live to YouTube. There will be a delay, but I'm not seeing any picture on YouTube yet.
Wait, will they know to join this one?
Yeah, we need to make sure, Taylor, we are in the same page with the.
I get it. No, it should be. This should be the link that's in the invite, but I am double checking. So.
Meeting. Okay, so when I copy invite link, the ID is 889. So it's 889. It's different from the one that we have on there.
On where?
On Eventbrite.
On Eventbrite? Okay.
Let me try and log in again to that one. Let's see.
Okay.
I think that one's not started. The one on the Eventbrite.
Yeah, no, it means I need to update it and email everybody.
Okay, cool.
It's giving the same error, invalid ID. Let's just change on the, let's just set it up here and change on the Eventbrite page.
That's what I'm doing.
You gave me the login for Eventbrite, right?
Yeah, I'm in the middle, Ankit, I'm doing that exact thing right now. It's okay, you don't need to. See, what I have, the one that I'm on, it's 821. That's where it doesn't make sense here.
This is the one that we are in.
Yeah.
85688. Let me check once, just a sec.
821 is the one that we're in right now.
Yeah, and that's what that's what I'm updating the Eventbrite to.
Yep. Okay, all good.
Okay, I'm just gonna email all the attendees. Yeah, this would have been a lot easier to do just as a webinar, but oh well.
So we should test our microphone is obviously working. Can you try muting and unmuting, Taylor?
Yes, I just muted you.
Okay.
But
So
let me test the mute all.
yeah, because I could unmute myself.
Yeah. All right, I see we have some people joining already. Welcome, everybody. We'll get started here in just a couple minutes.
Hi, everyone. We will get started in just 1 or 2 more minutes. All right, so we're going to get started. Hi, everyone. Thank you all for joining us. I'm Colin White. I'm head of research at Abacus.AI, and we're very excited today to put on this webinar where everybody will learn how to build a deep recommender model using Abacus.AI. So here's the agenda for this morning. I will start by giving a talk on deep recommender systems. We'll have a short break for Q&A, and then I'll hand it off to Ankit, who will teach all of you how to build a recommender model using Abacus.AI. Just as a quick preview, in case anyone's new or doesn't know too much about Abacus.AI, we are a cloud AI service where you can create deep learning models. So the way it works is you just go onto our website, which is Abacus.AI, and then you click on your use case, which can be recommender systems, or we also have fraud and security, forecasting, and so on. And then you use our easy to use interface to upload your data set and then do any advanced features you might want and then train a model. So like I said, you'll learn much more about that later on in this webinar. And so let's get started on the talk on deep recommender systems. Okay, so whether you know it or not, we are all interacting with recommender systems several times a day. Every time you go on to Netflix, Amazon, YouTube, or Pandora, we are interacting with recommender systems. So whenever you watch a YouTube video and you look at what the next videos are recommended, that is powered by a recommender system. And for these sorts of companies like Netflix, Amazon, YouTube, etc., recommender systems are very important. For instance, Netflix says that around 80% of all content watched by its users comes from personalized recommendations. Therefore, they want this recommender system to be as efficient as possible. If they improve their algorithm by just, say, 1%, then that'll result in many more users watching movies. Okay, so this is the outline of this talk. So first I'll sort of define the problem, the data sets, the metrics, and so on. Then I'll talk about some baseline techniques, and then later I'll get into deep learning techniques. Okay, so if you're familiar with some other sorts of machine learning problems like classification or regression, you might be used to having just one data set, but actually in recommender systems, there are typically 3 data sets. So for example, going back to the Netflix example, there's the user attributes, and that would be like the age of each person, their home country, their city, and so on. And then there's the item attributes. In this case, it'll be the movie title, the genre of the movie, and the average rating, and so on. And then finally, there's the interaction data. So this is the most important data set. And this is a big matrix where the users are columns, the items are rows. And then every single entry in this matrix is some form of interaction between the user and item. Here in this picture, the data takes the shape of ratings that the user gave that movie. And one thing to note is that this matrix is typically very sparse. So most users have watched a very small fraction of the total movies on Netflix. And similarly, for most movies, they're only watched by a very small fraction of the users. And so most of the entries in this matrix will just be question marks. And the goal for recommender systems is to fill in those question marks. So more concretely, one task we can think of is output a model such that every time we give it a user and a movie, it'll predict the rating that the user will give the movie. And another related form of this problem is output a ranking. So in this type of output, we take a user as input, like John, and then we output the entire ranking that we predict. Like what we predict their top choice movie would be, second choice, and so on. Okay, and another thing to note is this matrix here. They just have the ratings that they give the movies, but this can also be filled with anything. For instance, it can also have the timestamp that they watched the movie. It could even have a review of the movie if that user wrote a review, and so on. So this can be a much more complex type of data. Okay, so now I'll just talk about a couple different types of recommender systems we can have. For instance, the recommender system might have temporal data or not temporal. For example, if we think of the Amazon recommender system, a typical session might be a user logs on, then looks at 3 different coffee makers and buys one of them, then looks at 2 different filters buys that, and then starts buying beans once a month. So this data has quite a lot of temporal patterns. The user buys similar items at the same time, and we also have this recurring monthly purchase. Whereas Netflix, we don't see those sort of temporal patterns. We don't see like somebody watching a movie once a month. I mean, maybe there will be some temporal trends, but not quite to the same extent as something like Amazon. So the point is that there are just many sorts of types of recommender problems that are different from one another. So now I'll talk about how we split up the data into train and test. So if you're familiar with other machine learning problems like classification or regression, we just randomly split our data points. But remember, for recommender systems, we have a huge matrix. So it's a bit less clear how to do this. For non-temporal data, it's still fairly straightforward. Typically, what we do is for every user, we randomly split up all the items that user has interacted with into 80-10-10 split. For temporal data, it's a bit more involved. What we do is we select points in time that give an 80-10-10 split for all the total interactions. And then for every user, we look at which interactions fell before that time range. And the reason we do this is we want to be careful that we don't have test data leakage, where the training data leaks into the test set. For example, back to Netflix, if some movie got very popular in January 2020, then we don't want to just randomly assign interaction data because that movie might be in some of the users' training history, but not others, which would sort of give our recommender system an unfair advantage. So these temporal splits are the safest way to split up our data. Okay, and now typically what we do during training is we have our training data point, which is a user's history in temporal order, and then we try to predict the next item that user interacts with. And if a user has a history of size k, we can actually get k-1 data points out of this user by having the data point of all k-1, and then predict the kth item, and so on, all the way down to 1. Okay, so now I will talk about metrics. How do we evaluate these recommender systems? So the two simplest metrics are top n precision and recall. And so we can imagine the set of items that's the true top n. So for some user, Bob, their top n favorite movies in real life. And then we can also think about the predicted top n. So what our model predicts Bob's top n choices to be. And precision is the percent of items from the true top n that's also in the predicted top n. And recall is sort of the inverse. It's the percent of items in the predicted top n that's also in the true top n. Okay, now getting a bit more complex, there's NDCG, normalized discounted cumulative gain. And this is very similar to precision, but it weights the movies higher if they're higher up in the ranking list. So for example, it's more important to get Bob's first choice movie correct than it is to get his 50th choice of movie correct. So NDCG accounts for this. And finally, there's top n coverage. So for this, imagine if there's some recommender system that just takes the top 10 most popular movies and recommends those to every single user. So this is not very exciting because this recommender system is not learning the user preferences. And you might say, well, what if that is the actual truth? Like what if everybody does just enjoy only the top 10 most popular movies? If that's true, then we don't really need to be doing a recommender system. We can just output the most popular items. So typically a measure like coverage is a very good measure of how well our recommender system is doing. And what coverage does is it looks at the uniqueness of the top n items over the whole test set of users. So it's sort of gauging how much we've learned each user's individual preferences. Okay, so those are the metrics we use. Now I'll start to talk about some techniques for creating recommender systems. So the very simplest thing we can do is what I just mentioned on the previous slide, and that's output the most popular items to every single user. So of course, this is quite a naive algorithm, but it's typically good as just a sanity check or a baseline. If we're creating a brand new recommender system, we want to make sure it does better than top popular. The next baseline is k-nearest neighbor. So there are two types of k-nearest neighbor. For the first one, say that there's Alice and she likes these 7 books. And then there's another user, Bob, who likes 6 of those 7 books plus 2 more. So then we recommend those 2 more books to Alice. And the idea is that similar users will like similar books. And then item k-nearest neighbor. The idea here is that, say, Bob really likes this one book, then we look at other books that are very similar to that book and recommend those to Bob as well. Okay, so now I'll get into the third type of baseline, and that is matrix factorization. And this is actually quite a prominent algorithm. This was very popular in the 2000s. If you've heard of the Netflix challenge, this was a key algorithm in that challenge. And the way it works is that, remember our matrix of user item interaction is a very sparse matrix. So the idea is that we assume that this matrix has low dimension. And what that means is that we assume that it can be approximately, it can be approximated by these 2 skinny matrices, U and D, that you see here, or U and V, that each have dimension D. And so basically, this is kind of like we're assuming that there's a small amount of dimensions. For example, the user's dimensions might be whether this user likes action movies, whether they like comedy movies, their age, and so on. So we don't actually know what these dimensions are, but we do assume that they exist. And once we make this assumption, the whole problem turns into this big optimization problem where we try to find the best matrices U and V that makes the best approximation of our original matrix. Okay, so yeah, this tends to work quite well for non-temporal recommender system problems. Okay, so now just a couple other fine points. So one is this cold start issue. So say we have a great recommender system that's working really well, and then a new user joins Netflix. So then we have no previous interaction data because this user hasn't watched any movies yet. And the same thing can happen with movies. So say a brand new movie is just released, then it has not been watched by any user. So how do we get the ball rolling for these new users or items? And typically this is a very important problem that recommender systems have to solve. And we typically use a very different type of algorithm. Like we have our main recommender system, but then we have an extra algorithm on top of that that handles new users. And this will heavily rely on the user's features. Okay, and the same thing for movies, where we rely on the movie features. All right, and the other fine point is that AutoML is very beneficial. So the point here is that if you're familiar with, for instance, computer vision, where we train neural networks to classify images, many of the same techniques work across different problems. So the same techniques will work classifying images of cats versus dogs, then different types of plants, and so on. But for recommender systems, the different types of problems tend to be very different, and much different techniques will work for these different problems. And the reason is that there can be many different forms of recommender systems. I already talked about temporal versus non-temporal. There can also be the sparsity of the matrix matters. For example, on Netflix, the matrix is likely much more sparse than on YouTube because there are 2-hour movies versus 5-minute clips. And there are also other types of attributes of the recommender system problem that make different sorts of algorithms work better. And that's why something like AutoML can give us a huge advantage, because AutoML, or automated machine learning, is the process of automating this all these choices for what algorithm to use, what hyperparameters to use, how to get the best performance out of our model automatically. Okay. And that'll sort of tie into later in this webinar, where all of you will learn how to build your own recommender systems. Okay, so now I'll get into the deep learning techniques. And so first I'll talk about neural collaborative filtering. So this is a little bit related to matrix factorization, but we replace this matrix multiplication with a neural network. So the idea is that the inputs here are the user latent features and the item latent features. So this will be like the user's history and the item's history. So we pick a user and item, and then we feed it through the neural network. And then our neural network will output a prediction at the end, which will be the rating that this user would give this item. Okay, so we feed all of our training data into this neural network and train it so that it gets very good at predicting whether the user will like that movie. And another very common approach is neural matrix factorization. And that's just simply where we combine this approach with matrix factorization with an ensemble. So we do both approaches and then check the predictions for the matrix factorization and the neural network and combine these into our final prediction. Okay, so actually all of the methods I've talked about so far mostly just work for non-temporal data. So now I'll talk about some techniques specialized for temporal data. And for that, we can use recurrent neural networks. These are neural networks that take in data as a sequence, as a temporal sequence, and can learn temporal structures in our data. And the image in the slide here is a gated recurrent unit, which is a very popular recurrent neural network. Okay, so if we have some recommender system like Amazon, where somebody is ordering beans once a month, we probably want to use something like this. So the way it works is that we take in a user plus their entire history, as you can see on the left, and then we feed that through a fully connected neural network. And then we run it through this gated recurrent neural network where it'll learn the temporal patterns. Then we feed it through some more fully connected layers and finally output this prediction vector. And so this vector of predictions here, this gives a probability for every single item. And the probability is the probability that they will interact with this item next. So as you can see in this example here, the neural network will predict that this user has a 70% chance of interacting with this item next. And at the end, in order to train the model, we compare this vector to the ground truth. As you can see, the neural network did a pretty good job here. The one with the highest prediction is the correct answer. So then we take the cross entropy loss of these two vectors and backpropagate it through the neural network. Okay, so this is the rough idea of how this sort of setup works. Okay, and so next I'll talk about attention. And if you're familiar with natural language processing, there's an interesting thing that happened in the field where up until 2017, everybody was using recurrent neural networks, but then there is sort of a paradigm shift, and now everybody uses attention, such as transformers. So we can do the same sort of thing for recommender systems. So this is actually very similar to the previous slide, but here we replaced the gated recurrent unit with a transformer or a attention model. And the way attention works is that it's a separate neural network that points to the most important items in the user's history that were important for making the prediction. So for example, if a user on Netflix has watched all these movies and some of them are just very popular movies that everyone's watched, and other ones are these sort of niche movies that really define this user's specific preferences, then the attention model will point to those specific niche movies as being important in how it made its next prediction. Okay, so attention is a very efficient way of handling temporal data because it really points to the most important parts of the user's input. Okay. Next, I'll talk about some other types of recommender systems that might have more enriched data than just the rating each user gave the movie. So for example, let's think about Airbnb's recommender system. So the user data might include ratings that the user wrote out for the Airbnbs they've used. And the item data might include images because often the Airbnb hosts post images of their Airbnb. Okay, so just as a quick example, the way attention might work here is if a user has mentioned kitchen a lot in their reviews, then the attention layer will point to the part of the image that looks like a kitchen. Okay. Right, yeah, so attention might be a promising approach in the setting where there's more enriched data. All right, so now I'll talk about a few more types of approaches. So next, I'll go over variational autoencoders. So this again is similar to the setup I've shown before, where we take in the user and their history, and then we feed it through some specialized neural network. And in this case, we have an encoder and a decoder. So the way it works is the entire user history is fed through this encoder. You can basically think of this as a neural network that compresses the input down to just a small vector here in the middle. And then we have a decoder neural network that tries to reconstruct the original data the best it can. And the variational part is that in the middle here, when the vector is compressed, we add a little bit of noise here. And it turns out that this noise will actually make our neural network be much more robust. So the neural network will be able to train much better if we add some noise here. Yeah, and so then the rest of the setup is pretty much the same. But at the end, our loss function, which originally just had the cross entropy between the predictions and the ground truth, we also add the reconstruction error. So we look at the difference between this blue vector and this orange vector and add that to the loss function. Therefore, the neural network will try to make these vectors as similar as possible. All right. So now I'm almost done with this talk, and I'll end with just a few techniques that are sort of on the horizon. So these are two research papers. They're not quite an industry setting as I know it, but I think these are interesting techniques that are on the horizon. So the first one is this paper by King et al. In 2017. And they studied a recommender system that takes in image data. So as you can see on the left, there are images of shirts and pants and shoes. And so typically when a recommender system uses image data, one technique is we can learn a computer vision model, like a convolutional neural network. And once we have that convolutional neural network, it sort of processes the image into a vector that can then be used as the item features. But in this paper, they took it a step further and showed that if we train the convolutional neural network from scratch at the same time as we train the recommender system, then the performance becomes much better. And the intuition is that the convolutional neural network is learning fashion-aware image representations that can help out with the recommender system much better than if we had just used an off-the-shelf neural network. Okay, and the other really interesting thing that this paper did is they then swapped out the convolutional neural network with a generative adversarial network. And this is a special type of neural network that can not only classify images, but it can generate new images. And so if you can see this image, to the left of this dotted line, these are all images that the GAN generated itself. So these are products that do not yet exist. And so this is sort of quite an interesting direction to think about, that in the future, we might have recommender systems that can recommend personalized products for you that don't exist yet. And then maybe the most popular products the company then decides to create. Okay. And I'll talk about one other new type of research direction. And this is a paper by Chen et al. And they use a reinforcement learning based approach for recommender systems, which in its own right, reinforcement learning is a bit of a newer direction. And the idea here is that reinforcement learning allows, it's harder to set up. It's a harder problem than just a typical recommender system. But if we model every user as a reinforcement learning agent, we're able to more accurately model things like the user's preferences change with time and adapt and so on. So it's sort of a harder problem, but it could get us much better results if we do it correctly. And so again, this paper, they took this idea one step further, and they used this with a GAN to create synthetic users to help train their model. So they trained a GAN to create users that mimic real user behavior. And this is especially important for recommender systems that don't have a lot of training data, because these synthetic users will really help us train our model better. Okay, so those are just some interesting new research directions. Okay, so just to conclude, I went over the basics of recommender systems, the different data sets, the different metrics, baselines, and then I talked about some deep learning techniques and ended with some research directions. All right, so now what I'm going to do is check if there are some questions. So let me see. And after that, I'll hand it off to Ankit. All right. Does the neural network need to be retrained every time a movie is added? Yeah, so typically we don't need to retrain it every time a movie is added. I did mention the cold start issue, where if there's a brand new movie, if there are nobody's seen the movie yet, so we can have some special sort of algorithm on top of our recommender system, which sort of recommends movies in the first place to new users. Then once more people have watched it, we can just fit this movie into the recommender system. We do typically retrain the model every so often, but maybe like once a day or once a week, depending on how our set of items are evolving over time. But we don't need to do it for every single new movie. Oh, I see. Actually, Ankit already answered that. Okay, so let me look if there are any other questions. I think actually Ankit has helped out answering. So somebody asked about the CNNs and the VAEs. So yeah, I can go back to the CNN yeah, that was here. So yeah, so a recommender system might have image data, and this is a bit yeah, more enriched data than usual. So for example, this would be in the user history, or sorry, the item history. So if the items are all types of clothing, then we might have an image of that shirt. And then what we do is we take an off-the-shelf convolutional neural network that say this was a neural network that was trained on the ImageNet data. So then we take the first half of the layers, the types of layers that are just involved with finding the edges, finding the colors, finding the shapes, finding like the low-level features of this image. And then we just take the neural network right at that step, right after it's found these sorts of features that are like, these are the high-level attributes of this image. And then we can add those to the list of item attributes. And then I mentioned in this paper, they actually didn't use an off-the-shelf neural network. They actually trained it at the same time as they were training their recommender system. Okay. Let me see. So for the VAE, I see a question about adding noise here. So a variational autoencoder is actually a very popular technique. It works really well in areas of machine learning, for instance, fraud detection and other types of use cases. So I believe the way it works is that once we compress the original vector, all of these entries in this smaller vector are treated as a normal random variable. And so then we can just add a little bit of random noise, like half a standard deviation or something. I think the amount of noise you add is you need to choose the noise to best suit your problem, but it's modeled as noise from the normal distribution. Okay, so how do we maintain novelty, diversity, and serendipity in recommendations? Yeah, so I guess this is like a balancing act that the recommender system has to solve. But actually, many of the models I talked about will attempt to do this automatically. So inherently, when we train the recommender system, since the goal is to just predict the next item that the user interacts with, then it's trying to balance all of these types of features simultaneously. So for example, say this user always checks out new novel movies, then the neural network will learn that this user likes the really novel movies. And if some other user just likes the same old movies all the time, it'll also learn that sort of thing. Okay, so I think there are one or two more questions, but I might be going a bit over time, so maybe I can just answer the rest of them in the chat. Okay, so with that, I'll stop sharing and hand it off to Ankit.
Thanks, Colin. That was an extremely nice and detailed talk on recommender systems. And that was really enjoyable. So from here, we will start our demo. So as I told you in the chat, we will be training an anime recommender system live using Abacus.AI platform. And let's get started. So I've already shared the notebook link with you all. Let me share it again, just in case there are some people who might not have marked it. So this is the Google Colab notebook link where all the resources that we would be using for this demo are present. So please open this. And then you would see a sign up link and some resources. So those are the data sets. You would fetch your data sets from there. And then some slides you have already seen. And that public data set reference is actually the link from the Kaggle, because the data set that we'll be using is basically taken from Kaggle. It's an open public data set. And you can later refer in the Kaggle if you want to know more about the domain of the data set, but I'll be explaining whatever you need about the data set as well. Like what are the columns in the data set, how we'll be utilizing them to train the recommender system. And then we will like go end to end, right from uploading data to generating predictions and then analyzing the quality of the predictions. So let's first sign up for the platform so that we can start training our model. So let me quickly share my screen with you all. Okay, hope you all can see my screen. I'm just adjusting a little here. Okay. So is my screen properly visible? Can you please confirm once? The chat is not coming here. Okay. Yes, great, awesome. So many yeses. Okay. Okay, so again, my name is Ankit. I introduced about a lot of things, but not about myself. So my name is Ankit. I'm head of content and developer relations at Abacus.AI. We are a deep learning first company, as you might have already understood by now. Our technology is primarily concerned with deep learning. Everything that we use is somehow related to deep learning. And that's why the title is Deep Recommender System, because we will be training a deep neural network that recommends things under the hood. So with that, let's get started with the sign up process, because that's the preliminary. But without that, you would not be able to use the platform. So be very careful in this step. And if somebody lags behind, just let me know and I'll repeat as needed. So you just have to click here. So here I'm already logged in. So that's why it's coming like here. So let me copy this. For you, you just have to click nothing else. And then I'll open a new incognito. You don't have to do that because you already are not registered with the platform. So it will take you to something like this. Okay. So here you will enter your name, your email ID, password, one uppercase letter. Okay. So after you're done filling all the 3 fields, your name, an email ID, and an associated password that meets all the criteria, a special character, an upper and lowercase, and probably a number too, and minimum 8 digits, then you would be ready to shoot this sign up button. Okay, so I'm going to click on this. Okay, here I go. And then org name, this is like the name of your organization. Let's say you have a team, you want to name that team something like Team Recommender, Team Rexus, something like that. So this will create a container where you will be able to keep your projects and then train models under those projects. Okay, so you enter your organization name here, and then you click on this. Now we are in. This is our org. This is my name. If you click here, these are your email preference settings for this organization. If something fails, if your model gets trained, or if your data set processing fails, you'll get notified on this email. Okay, all these functionalities are here. You can add your teammates here by sending an invitation link. If you add a Google Cloud bucket or something, then that will pop up here. This is your API key. Okay, so coming back to the welcome page again. So now we have our organization set up. We'll start creating our recommender system. So for that, we'll create a new project. So Recommender AI is a solution that Abacus.AI provides. And then we provide 3 different types of recommender AIs: personalized recommendations, related items, and personalized re-ranking of lists. So if you want, you can later read about these use cases in detail. There are snippets for a high-level overview, but if you want to go into detail, you can always click on this documentation button, and then you can go about reading. So for the purpose of this demo, we would be utilizing this particular use case, personalized recommendations, because what we are going to essentially do is train an anime recommender system, as I already shared before on the chat. So this anime recommender system is based on that Kaggle dataset that I showed you, the link to which I showed you. So what it does is based on the interaction that the user has with a variety of different animes, it generates what is the likelihood of user liking some particular anime. So that's sort of a personalized recommendation that is being personalized for the end user, right? Like because of some preferences that he has shown in the past, he would be now recommended with something new. So that's a personalized recommendation. So that's why we're going to choose this use case and then start training our recommender system under this use case. So for every project that we create on this platform, Abacus.AI, we have to create that project under a specific use case. And that makes it easier to start the process because now you have like a set template, and that template will tell you which data set to upload, what are the requirements of those data sets. So you'll see how, okay? So it becomes easy because a lot of times what happens is it gets tricky to start with machine learning and deep learning. Like you never know how your problem is going to be solved using deep learning. So if you have a framework, it gets a lot easier to start. So with that, let's start with our personalized recommendations use case. Click on continue. Project name, anime recommender. You can just name as per your wishes. I'm just using a random name that I feel is cool. Okay, let's click on finish. Okay, now this is what I was describing. You get a template, like this is the template that these are the 3 data sets that you might be willing to upload or attach to this project under this specific personalized recommendation use case. User item interactions, catalog attributes, user attributes. So user item interactions is the interaction of the end user with the anime in this case, which is required because if you don't have a history of interactions, how are you going to even learn a new model, right? So that's why it's required. And then catalog attributes, which means like your anime might have their own attributes, like how long, how many episodes are there, how many users, how many community members it has on some social media page. So a lot of such catalog attributes. In our case, anime attributes. User attributes. The user might have his age, his demographics, and a lot of user attributes. So this data set might have user attributes. So for this demo, let me show you. We will have these 2 data sets, anime rating data set and anime metadata. Okay, which will go here, anime rating here and anime metadata here. So let's start by uploading the data sets. So for uploading the data sets, what you will have to do is go back to that collab notebook that I shared here. So now I hope everybody is very clear with the sign up process and they have already signed up. Let me quickly bring the chat again. Oh man. What if we do not select organization name? So organization name is necessary. As I said, whenever you sign up, you have to make an organization which belongs to like a team, which might be working on one project. So organization is just a container where you have a lot of projects or just one project, depending upon your needs. And then under that organization, you train those projects. So that's why we need to have an organization, because generally AI is like not an isolated activity. We do it in teams. A group of people do collaboratively work on such problems. So that makes sense, right? Yeah. Do personalized recommendations and personalized ranking of lists use the same underlying neural network? If not, how are they different? Yeah, as I said, you can always click on that documentation button and that will take you to individual documentation for each of the use cases that we offer. And that way you would be able to know each and individual problem type that the use case solves. And you can even read the type of data sets that they need, the type of outcomes that they produce, the type of training options available under them. There's a lot of literature on those things. So if I go into like a deep dive on each of those things, then we are done with this demo. So I hope you understand and you would like try reading those documentations and shooting me an email whenever you need any clarity on those things. So for the purpose of this demo, I will just keep myself restricted to personalized recommendations for now. And since you all seem to have signed up, let's start our process of training the deep learning based model for this anime recommender. Okay, shifting it a bit down again. And so click on this anime rating data set. Download using this button. Here it goes. Anime ratings are in my computer, on my computer. Now the metadata. So downloading this as well. So both the data sets that we need are here on our PC, anime metadata and anime ratings, okay? So once we have both the data sets on our PC, we're gonna upload that to Abacus.AI platform. So you would click user item interactions. That's the first required one. That's absolutely required because, as I said, without the history, you can't train a model. So click on create new, name this as anime ratings because users have given ratings to the animes and this data set encapsulates that all. User item interaction is the dataset type. Click on continue. Now you can simply, for you, since you have not opened the incognito, it will be just here, right? So it will be a lot easier for you. You just have to, you just have to like click here, anime ratings, and then just drag it here, and your anime ratings will come here. And then you have to click add dataset, and it will start getting processed. So it will take a little bit of time to process this data set. It's around 33 MB. So most of the time is taken to processing, not upload, because uploading is fast, just 33 MBs. But processing is an involved process. So that will take some time, like a couple of minutes. Okay, so by that time, we can do something like uploading the second data set. For that, we can just open a new tab. Go to Abacus.AI, click on our dashboard. And here we have our project. Click on the project. Okay, so you can see this is getting inspected here. So for those people who don't want to wait, you can come here. And then now we are ready to upload the catalog attributes. So catalog attributes means, in our case, the anime attributes. So create data set, create new, anime metadata. So this is the metadata for this anime list, the catalog of anime that we have. Continue. And again, we can upload our second anime metadata here. Or there's another way. You can just click here and go to your location wherever you have downloaded it, and then select and click on open. Okay. So anime metadata.csv file and add data set. Now the second file is getting inspected. So you see now that OK button popped up. So second time it might pop up, not the first time, because the system is trying to tell you that, hey, wait for the inspection to complete, and then only we can proceed forward. So let's now dive into what inspection does. So you see all these different screens. We have two data sets getting processed. Once this gets processed, you will see schema screen getting populated, raw data getting populated, data exploration getting populated. Okay. And data prep also will get populated. So in order to do all those things, the system has to execute a lot of internal processes, like read the schema, read individual columns of the data set, see what are the values in those columns, what are the data types of those values, how should it categorize those data types, those data values, and then how should it map those data column values to something that is recognized internally by the system. So all this is getting done at the back. So that's why it's taking some time. So now we see one data set is populated. So all you have to do is come here at your anime recommender main screen. And then, so ratings got populated. This is the first one. So as you can see, item ID, user ID is checkmark, timestamp is checkmark, but it's all yellow. That means system has identified, but it's trying to ask you that, hey, I have identified this like this. Is it correct? So it's like a verification step where the system is trying to ask you to verify what it has recognized already. So let's confirm this. Confirms. We'll click on confirm schema mapping. So for this, item ID is our anime ID because anime is our item for this specific case. Confirm. User ID is our user ID. Confirm. So now it's successfully mapped. It turned green, as you can see. You can go here and see it turned green. So that means one data set is successfully mapped. See, now it's asking us to train the model. It's saying that, hey, you can now train the model. So if you carefully notice in the beginning, when we created this project, it told us that, hey, this is the necessary data set to upload, and all these are optional, right? So now it has the necessary data set, so it's allowing us to train this model. Otherwise, it won't. Okay. So I told you already, this is necessary because it has all the historical data values that we need to train a new model. Like it has all the user anime interactions. That is what we need. But for enhancing the performance of the model, if we have the attributes of users and attributes of anime themselves, then it will be even better because the system will have more context on generating good predictions or recommendations. Okay. So that's why we uploaded this catalog attributes as well to make it better. It's still getting inspected. It will not take much time, I'm pretty sure. Because if you see the, it's just 936 KB. So it will populate pretty soon, I'm sure. Okay, it's active now. If you go to the dashboard, you will see anime metadata being active for confirming the schema mapping again. So confirm schema mapping, anime ID is item ID in this case, confirm and continue. So now we have this data set mapped as well. Okay, now let's, as I said, all these interfaces will get populated. So you can see they're getting populated. They already got populated. So now let's analyze the data a bit so that we will know what we are training, because without even knowing our data, it's not a nice idea to start training the model. Okay, so click on the schema. We have anime ratings. So this is how the schema looks like. User ID, which is mapped to the user ID. So this is the system identified mapping. That means internally, the system, like your column ID, your column name might be something very substantially different from something that is standard. Like you might have people ID, you might have people name, person name, whatever. So system needs to map it to something that it recognizes. So that's why it has mapped to this. For anime ID, it's item ID. Rating, it's nothing. It's because it's like, we don't need to map rating. Rating is like, the system will automatically know that it has to, that it has to rate, like this is the rating for the anime. And that is how it has recognized this as categorical. Okay, so these are some of the other mapping types, because there are different kinds of recommendation systems, as Colin discussed during the talk, and they might require some other kind of mappings. And if you want to dive into these sort of scenarios and their descriptions, you are always welcome to read about them in the documentation center by clicking here. Okay, so for this demo, we only need these mappings, and we only need to understand these three things. What is user ID, what is item ID, and what is timestamp. Timestamp is nothing but the time at which the user might have interacted with some anime, specific anime. So that is the timestamp. And that is the rating the user might have given to the anime. So quickly, let's analyze. Now we know the schema of this data set. Let's also get to know the schema of metadata. So metadata has anime ID, okay. And then the anime name, genre, type of anime, episodes, ratings, and members. So members is like, how many members do this anime have in its community? So they might have like a social media community for that anime. So there will be like some specific number of members in that community. This denotes that. It's a numerical type. Ratings is numerical because the greater the, like a smaller number and a larger number, to distinguish that, we will have it as a numerical data type. But for episodes, smaller number, larger number, that concept doesn't make sense, right? Because episode 1 and 2, it hurts to say that, hey, episode 2 will be better than 1, right? It cannot be the case every time. So that's why these categories are like at equilibrium. So that's why we will have this categorical data type for this. So when the sequence matters, then we have numerical. A lot of you people already know that if they're coming from machine learning background, but for people who might be new, it's a good idea to like tell them what categorical and numerical are. So that's why I explained briefly. Something where the order makes sense, where the previous value is greater than the other value, then you would have numerical. For something where you have equally significant categories, you will have categorical. Okay. Categorical list, you will know why is it a categorical list. And anime ratings also has this, which is quite clear. So now let's see our raw data. It will make more sense now if you see the raw data. So user ID, anime ID, ratings. So -1 is for people who have watched it but not rated. So that's why it's -1. So on Kaggle, if you want to read about the domains, you would be able to, you will get to know that what -1 is. So I've already explained for now what you need to know. Rating is -1. That means user has rated this. User has not rated this, but watched this anime. But otherwise, it's like ranging from 1 to 10. You will see if you go down, there will be a lot of other values like 7, 6, 10. Timestamp. So I think now it makes sense, all this data to you, right? Let's also visualize anime metadata. Okay. If you click here, it will come here. So anime ID, name of the anime, genre. So you see what categorical list is, action, comedy. So it's not just one category, it's a list of categories. So that's why it was categorical list. Type, TV, episodes, number of episodes, ratings, members in the community, this much. So now you're familiar with what your data looks like. We can move ahead to this data exploration tab. So this is your data exploration. It's like a little bit of probability and statistics in here. All those things like, distinct values in this column, the mean, min, max. If it makes sense, then it will be populated. Here it doesn't. So it wasn't populated. These are the value distribution graphs. You can check like for this particular value, what is the probability distribution? All that is shown here. Okay. Okay, now this is another new cool feature. So I'll explain this a bit, but we're not going to use it for the purpose of this demo. But yeah, you can later find some time to play with these features and train more models. So let me quickly explain what it does. So a lot of machine learning. So for machine learning, we do a lot of data prep. Like it's a very important and significant step in machine learning process and like process of training new models. Like for example, you might be interested in, let's say, creating a new column. Like we have these number of columns, but you might be interested in creating a new column that might hold some new information. Like for example, you want to create a correlated column between the episodes and the ratings. Like, oh, highly. So you want to see cumulatively, like what the episode looks like, how the ratings looks like when there are like some certain number of episodes, right? You want to like have a correlation there. So you might create a new column, merging these two columns, and then kind of like training your model on them, right? So there are a lot of like machine learning techniques that require you to add or remove correlations between columns, which you can do using all these, using this custom column feature. Data prep is like, let's say in this raw data tab, you have some user who always leaves the data unrated, like he watches but doesn't rate the data. So you want to exclude this user so that his data, his rows are not taken into consideration for model training. So you can do using this filter. Like you can go here, you can click on exclude. You can write user ID equals to 1. You can preview. You see user ID 1, anime ID this, rating -1. So now this user ID will be excluded from the data before training this model. And now you can save it. So now this criteria will be used to filter your data before training the model. So that's how you can make use of filters, include and exclude filters. So for the purpose of this demo, we're not going to use them for training. But yeah, you can definitely play and come up with your ideas and see how it changes the predictions. Okay. Same we can do with the custom column. We can add a custom column, give it a new rating, like let's say new _ rating. You want to give this column this name, and then you want to write some condition for generating new rating. Let's say, let me just show you real quick. Like let's say you have a case where whenever the user has -1, which denotes like he has not watched, you want a string like none in there. So you can have something like case when rating equals -1. Sorry, my bad. Here. Then none. And so whenever this column will have -1, we will change the value to none. And we'll have a new column which will have none values for -1 and the same values for the other. Okay. Or you can just write, to make it more clear, else rating. Even if you would not have written it, it will still make sense. But yeah, just to be clear, like otherwise, we'll just keep the value rating in this new column. Okay. You can preview. See none, none, none. So your data is populated with this whenever there was -1. Now you can add it. So I'm just showing you like to give you ideas on how you can make use of add custom columns and filterings, and then later play with all this. Yeah. So now you see there's a new column, and you can ignore the old ratings now. Ignore. That means this data column will not be taken into consideration for training this model that we're going to train. So we can ignore this. We can have this. So now you can train using all this configuration, like go here, train. But for the purpose of this demo, I'll just simply train without these conditions. So deleting this. Okay. But yeah, I think you got the idea, like how data pre-processing can be done without writing much code using this interface and these new cool features like add custom column and including and exclude filtering options. Okay. So enough on the data side of things. It's very important. So I wanted to like take some time to dive deep into all these possibilities that you have with this platform and how you could play with the data to get the best output and, utilize most of your creativity. Okay, now let's train the model. So going back to the main page, we are ready to train the model. So clicking on this train model button will start the process of training. So now it's asking me the configuration that I want for the training. It's the default name it will give if I don't write anything, let it be default. And we'll simply click on train model. So it will take some time to train this model, like maybe an hour or two, because at the back of the scenes, there's a lot that goes on into training this model, as Colin highlighted during his talk, like what kind of things happen at the background. So that's a lengthy procedure, so it's bound to take some time, right? So once this training gets completed, this interface will be populated, and then you would be able to deploy your model, the trained model, and then generate predictions from that. So in the interest of time, I will definitely not want to wait for this training to finish. I would rather want to go to the finished product and show you guys what you could do once your training gets completed at your own PCs. Okay. So I hope you have walked with me this far. Let me again check the chat real quick here. Okay, I'm going to answer all these questions for sure at the end. We will have a specific dedicated time for Q&A. Yeah, but for now, let me jump to the already trained model and show you guys what can be done when your model is trained. Okay. So I'll open a new window here. So this is a different org, Abacus.AI workshops, where I keep my trained models for the purpose of workshops. So this is the same exact thing, the same exact project. The only difference is the training has been completed. Okay, so now you can see these two interfaces are populated. There's a trained model here. It shows the time when it was trained. It gives you options to retrain or go to the metrics page. And then since I created a deployment as well, it gives me this option to go to the predictions and visualize the predictions that are generated from this deployment through this deployment, or go to the APIs and then play with the API. Okay, so I will go to this page for now. So this is the model that was trained, anime recommender system model. And this is the date, it's complete. If I click on it, it will give me the details of this model. Like what is the version, what are the data sets version associated with the model. If I have a deployment associated, then it will give me the deployment that is connected to this model. The provisioned QPS, 5 calls per second. So you can click on these question marks whenever you have any doubt on what this is about. So for people who might not have familiarity with all these things, they should feel free to like use this in-product help to make sense of the various options that are available on the UI or various things that they might not be so familiar with. So let's click on this metric page and learn about the quality of the trained model. Because once we have a model, it becomes imperative to see how good it is. And we'll see it using this dashboard, the metric dashboard. So for advanced people who are deep into machine learning, they can click even here and get like even more details on the scores. But yeah, this interface shows a lot still. So let me walk you all briefly through the major metrics and the principles behind those metrics so that you would get an intuition of what these numbers mean. Okay. So before that, I would like to add personalization popularity baseline is the base model. So we need a reference to check how good of our model we have trained. So this is the reference that we have in this product, personalization popularity baseline, which is just a popularity baseline, which just means that whenever a system recommends popular items like that are most frequently bought by most of the users, then that's just a very common kind of recommender system that all the time, without taking into consideration the personalization for some specific user, just puts out everything that is popular because it's popular, so it's likely to be bought, right? So something like that. So for the anime, this is the baseline, the popular anime baseline. And these are the scores. And these are the improved scores of the model that we have trained. So let's now delve into the metrics. Normalized discounted cumulative gain, NDCG, one of the most popular metrics for evaluating recommender systems. So ranking-based recommender systems, they're properly, like this metric is kind of good at evaluating them. So as you can imagine, in the list of predictions or recommendations that are generated, there's a rank, right? Like the most popular thing and the second most, the third, so top and rank. So it's basically a ranking-based system. So that's why these ranking-based metrics are being used. So NDCG is nothing but it just gives you like a number from 0 to 1, where the higher number is better, such that whenever the ranking is relevant, like it's close to the ground truth, then the number is high. But there's a specific mathematical form associated with it. And you can dive deeper into that form if you're interested, like why the score of 0.32, why not less, right? And why the ideal range that you see in typical recommender systems is 0.15 to 0.4, right? So it's like close to the ideal range. So it's like a good recommender system, really good. But for getting an intuition, you would have to dive a bit on like how it gives this, how it like outputs this number. So the principle is quite simple, that some items are more relevant. So if you rank them highly, then the score should be high. Some items are less relevant, so you should rank them low. So that is the principle, like rank the most relevant items high up the list. And that's a reward scheme. But then there's a specific mathematical form that it uses. You can like dive deep into that, but that will require some time. So in the interest of time, I would not go into that. But yeah, for now, this intuition should be enough, like how it spits out a number based on the relative ranking of the output. 5 and 10 is nothing, but like it's only the 5 top contributes for the calculation. Here, the top 10 contributes for the calculation. Same with this, but here map, it has a different mathematical form. The principle is also slightly different. So it computes the average precision over all the users. Okay, so what it does is, like, in simple terms, it's the same. If you rank the relevant ones up, then you are not penalized, then you are rewarded high. And if you are ranking the relevant ones lower, then you are basically not rewarded high. But then again, the average precision is the mathematical form that differs here for all the users. So if you want to dive deep, again, I would suggest you to go and visit this link and see how this average precision is calculated, how it's then further, and how the penalization happens for those incorrect guesses. But yeah, 0.001 to 0.01 is the range. So as you can see here, you're getting 0.01, 0.09, which is kind of very high. So it's a very good recommender system. Now we have mean reciprocal rank, MRR. So there are some recommender systems in which the top 2-3 items matter the most and rest is like garbage. So for those cases, people pay attention to this mean reciprocal rank because this is heavily based on whether the system is getting those top 2 or 3 items right or not. So that's the criteria for mean reciprocal rank, whether those top 2-3 things are fine or not. So you can again see the mathematical form if you want. But yeah, that's the basic principle. Personalization. So somebody in the chat asked like this diversity things, serendipity, and I don't know what those words were. But yeah, that was an interesting question. And the answer lies here. So how is your recommender system personalizing the things? Because as you can see here, this popularity thing, what it does is just spit out all the popular items for any user, right? There's no personalization. But here, for every user, based on his watch history and the interaction history and the ratings that he has given to those animes, there's a personalization factor involved. Like for him specifically, some specific set of animes will be recommended, not the other animes, depending upon the level of personalization that the recommender system produces. So this is the metric that tells you that how far the system went into personalizing those things for the specific users. So 0.9 is kind of really on the higher side. You would definitely see something like 0.4, 0.5 in typical recommender systems. But yeah, this one is, I think, well-trained. So 0.9 is really good. Really high level of personalization. So if you will change the user ID, you will always see a new set of animes being recommended based on his watch, his interaction with the set of animes in the catalog. Item coverage. So this again answers that question. Item coverage is like the whole catalog might have like thousands of animes. So how many animes were recommended out of those thousands? So that's the coverage. So 0.16 is again a good amount of coverage. It ranges from 0 to 1. Generally, you see like 0.00 something, 0.01, 0.05, something like that. 0.16 is kind of good. And the more items the recommendation system covers, the more it suffers in all these metrics because now it's covering a huge breadth of items. So it might not be able to like produce good recommendations for all those users in our data set. So these metrics might suffer. So generally it's seen like if the coverage is high, these numbers go low. But with 0.16 coverage, these kind of metric scores are kind of really good. So this is definitely a good recommender system. And if you see the amount of data we had, let's see, 1,000 rows for ratings we had only. Like if you go to the Kaggle, they're like, I think a million. So we have only taken like what, 10% of the data? Yeah. So yeah, you can try and see. And 12,000 was the anime attributes. So you can try and go there and see if you increase the amount of data, does it improve the results or not? Like you can go and play later. Okay, now I think you might have some sense of what these metric scores are and what they signify. So you would be in a position to like make sense of the quality of this recommender system that we have trained and the ones that you will train in the future. So these graphs show the same things. Here it's map, here it's NDCG. Okay. Okay, now let's move on to the final part, which is the predictions themselves. So if you see the deployment, this is the deployment that I created. So for you, it will be blank, but once your model gets trained, you would be able to click on some buttons and then create this deployment. And this deployment is nothing but like a container which you can utilize to generate predictions. So your predictions are generated through the deployment. Deployment is like there's an infrastructure on which you need GPUs, right, for training the model. Similarly, you need some infrastructure for generating predictions from your trained model. So that is the deployment serves that purpose. So if you click on the deployment dashboard, you will see something like this. And this is the user ID, which belongs to some user in the data. And this is his watch history. Like this is the anime he watched. And this is the prediction that the system has given. So these are the recommendations that the system has produced. So 50 for this guy. If you change this, the recommendations should change. See? So yeah, this is another way to like get a sense of how diverse the system is by like looking at these lists and kind of seeing like if you are familiar with the anime, you watch a lot of anime, you would even make sense of like what these animes are, what categories are they into, and then see, oh, is this associated or not? So you would be able to see like if somebody likes Attack on Titan, then somebody might like something close, right? Like maybe Alchemist, I don't know, or maybe like One Punch Man. Yeah, so you can use this dashboard to like make sense of those kind of things as well. Okay. So yeah, there's this one more thing I would like to highlight. If you click on that button at the top right corner, you would come here. And this is another quick recommendation system evaluation guide, which you can read on if you would like. And there's a blog post as well that I've written. So you can go there and read even more on that if you would like, if you're interested in recommendation systems. So some people might come from software development background, software engineering background, and they might want to utilize this API to embed these predictions into some of their web applications or desktop applications or whatsoever. So they can like use our APIs, something like this, and they can get the outputs and they can have like a picture of anime and then something creative they can do. Like they have a web page, they can like have you input your favorite animes and then the system recommending some other anime. So a lot of creative things can be accomplished using your applications and then embedding them with our AI using this API. So the possibilities are endless. You just need to be creative. You just need to be interested and passionate. Finally, there's something called batch prediction. Batch prediction is nothing but you want to batch your predictions into one unit, and then you want to get them into a file or some bucket on the cloud. So you can do this using here, like my bread set one. All IDs means all the different data animes and the users in the data set will be considered. If you want some specific list, you can write here those IDs, and predictions will be generated only for those specific animes or users. You can have a file, or you can, if you have your bucket connected from GCP or AWS, you can point it to there and the predictions will go there. Refresh the schedule is like as Colin said, a lot of times the data set gets updated. So you have refresh schedules for all those things, like automatically at that specific time that you will enter, the system will generate predictions. Like every Sunday at noon, it will generate. So if you write this cron string there, that is going to happen. The prediction batch prediction will be generated at that time. So things of that sort. If you click here, you will get your batch prediction set. Same for model. You can set a time for a model using this here. Again, a cron expression, and then the model will get retrained, and that's at that specific schedule that you will set here. Like, yeah. So you can go, and this link will help you generate that format. Same with the data set. If your data gets generated, if you have new data coming in, then you can set a schedule in your data set, and then it will give you the option to like take your schedule and then refresh the data set automatically without you having to go to the interfaces and like clicking on the upload button and doing all those necessary things. Okay. So yeah, I think that ends the demo. I have shown you end-to-end process of like how you can go about uploading data, making sense of your data, doing data filtering, adding new custom columns, training models using your uploaded and manipulated data, and then evaluating the metrics of your trained model, evaluating your trained model using the metrics that I explained, and then finally deploying that model into a serving environment to generate predictions out of them so that you can enjoy your predictions or your recommendations. So with that, I think I'll conclude this demo, and I would welcome any questions that you might have for me. Okay, let's move to the chat. Do you have plans to support multi-criteria ratings in the future? Multi-criteria ratings, I'm not sure. Like you're trying to say something like, instead of a number, something like there are some categories and then they have rated the anime in those categories. Like let's say how entertaining it was, or some other parameters of like evaluating the anime, right? Like instead of just a one number being used to rate the overall anime, like 5 different categories, like what is the quality of production, right? Or what was the length? Was it overstretched? So these kind of, yeah. So you can do this. So as I said, if you have this kind of data, then you can play with your data and make custom columns, or like tweak them depending upon what you need exactly, and then you can upload on the system, right? And then you can map it as I've shown you during the demo, and then use that kind of mapping and use that kind of criteria to like have your target variables being rated by the system. So you would have like, instead of one rating, you would have like a recommended rating in those 5 dimensions. So it's definitely possible. You would have to do some tweaking before uploading the data, but that is definitely possible. And we always come up with things like that. Like if somebody has that kind of use case or scenario and they ask us to develop something, then we definitely look forward to developing those kind of modules. But yeah, since I think we don't currently have that sort of scenario, that's why, yeah, I've never come across that sort of scenario yet. So that's why the interface lacks that kind of things. But yeah, if you can tweak the data, you can definitely have it done. I guess the basic ones are nearest neighbors or clustering based. Can we get the recording? Yeah, the session is being recorded. It will be available in some time for you to refer to. How to upload, push new data sets to the platform. Is there a way to update data sets automatically as new data is generated? Yeah, I already shown you those cron expressions and how you can do it at 3 levels. One is the data set level, one is the model level, and the third one was batch prediction level. How to practice one on Colab or any other platform? Okay, so for that, you would have to know machine learning, and definitely you would have to like write a lot of code on data preprocessing, and then finally your algorithm you would have to implement or use some other library that does it for you internally, like scikit-learn. And then you would have to feed all your prepared data into that library, connect the 2 of those things, and then finally get some recommendations. And then you would have to also think about your deployment and the amount of load that you would be able to take with that deployment, the GPUs and stuff, the infrastructure, if you have that or not. So yeah, a lot of machinery goes on into developing all these sort of things, as well as a lot of knowledge is required to get it done. But yeah, the idea here was if somebody lacks the domain knowledge, or if somebody doesn't come from a machine learning background, how they could still express and display their creativity with recommendation systems by using such a service like Abacus.AI. Let's see what else. Like a movie has story, visual, etc., as well as an overall thing. I'm not sure what it is. Aren't you going to show in Colab how to train in Python? So the whole process I showed using UI because I wanted to signify how the process can be made so easy, like how you can get to predictions with just a couple of clicks, with just a very basic knowledge of what recommendation system stands for, and with some basic knowledge of how to evaluate a system, how you could like make sense of a public data set, a publicly available data set, and get to the prediction stage in just like an hour, right? So that was the whole idea, like how to train an end-to-end deep recommender system, and how to make sense of those public data sets and get some real high quality predictions out of them. So it was like teaching you recommender system on a high level, where you can not only make use of public data sets, but also get some intuitive understanding on how to evaluate the predictions that are being generated from by using those public data sets, publicly available data sets. and how like an end-to-end deep recommender system might work like in a real world scenario. So that's the idea here. But yeah, if I would want to like go into like the development, then it would be like crazy number of hours, like, you know, like discussing about those algorithms, just discussing about the pre-processing stages, discussing about deployment and how the machinery inside batch prediction works. And then it's going to be like crazy amount of work. But yeah, if you're interested, there's a lot of resource online that you might eventually jump upon and possibly utilize. What is happening at the back end? Like what models we are using? So in the talk with Colin, he mentioned the different techniques. So all those techniques are actually being used in the system. There's nothing new. Like how we use CNNs, how we use a feed-forward neural network. He like kind of went through all those things. So the same principles are being used. So it's not an RL-based system that we are utilizing, or an encoder-decoder type system. What was it? The autoencoder. That's not something we are using. We are using CNN layers, definitely. We are using a feed-forward neural network. So all those things are being used. Is it completely black box system, or is it a way of knowing what kind of model was selected and the hyperparameter value selected? Okay, so deep learning is a black box in the sense that what are those connections that were made and how the system made it is quite a black box. But then there are methods to white box them to an extent, like explainability. So we have an explainability model that shows a bit of it. So there's a workshop that you can find on our YouTube channel that explains on those lines. You can go through that. But yeah, it's an involved process. So you would have to go through that parts of that workshop to understand how explainability works for such systems. Hyperparameter values like so for advanced machine learning practitioners, we do have advanced training options. So I skipped this because that would require extensive understanding of the system, like and the machine learning itself. So that's why for the purpose of this demo, I didn't show them, but I can quickly go through some of those advanced options if you would like. At the end of this session, if we have time, I would definitely do that. So using those advanced options, you can tweak like batch, like you can tweak the input size of the batch, the learning rate, the dropout rate, all those things. You can tell the network how much history it can take for training the model, for training itself. So you can set a lot of those hyperparameters using the interface that I showed you before. Like you click on train the model, you can click on the advanced options and select all those parameters yourself. I would encourage you to use a gender neutral pronouns when describing users, at least he, she. Yeah, sorry if I might have missed that. I try to like, for the sake of simplicity, I might have just used he, but definitely, yeah, he and she both are welcomed. I don't see a place to put credit card or some cost of estimation. So when we conduct these workshops, we allow you to use the platform free of cost for like at least 5 training models, I must say. But yeah, after that, you would be required to register using your credit card. Did anyone have trouble with the ratings file? What common errors can we expect in inspection? Do you have plans to support? Okay, so I think I've covered. I'll go down. There are 5 new messages. Here's the talk on AI explainability service. Yep, Colin already shared that. Image processing can be done using convolution. Okay, process would be the same for image datasets too, right? No. So we right now are supporting tabular datasets. For image datasets, Colin have a slide where he explains like how image features are captured, and then we can utilize those captured image features as well. So yeah, so for putting it into our system, you would have to do a lot of pre-processing and capturing. But yeah, we would definitely have some sort of thing in the future to do cool stuff with the images and even audio, or even some other modalities like language. Does your backend use TensorFlow or similar API? Yeah, it's primarily TensorFlow, you're right. data anonymity. Okay, so we have SOC 2 already implemented. We are going towards FedRAMP. So definitely there's a lot of data security that we provide. What else? Implicit data instead of explicit, such a user viewing a product or rating. Implicit data sets. What about implicit data sets instead of explicit, such as user viewing a product or rating it? I'm not exactly sure if you're trying to say that at the real time. So yes, we support streaming APIs and streaming functionality where at the real time, the user is rating a product or viewing a product and the data is going into our system at the real time and the predictions are being generated or the recommendations are being generated and then populated to a group of entirely different users. So the system will be like trained on the similarity of those users and recommend. If 2 users are same, then similar products will be recommended. If they're different, then different products will be recommended. So such things. So we have some customers which have such use case scenarios, and we do that definitely. It's possible using this technology. Okay, what feature store functionality do you offer? Yeah, so we have recently came up with our new feature store. So we would be putting an explicit page on our website soon that will like deeply include all that you need to know about the feature store functionality. Is there a switch one can flip to direct the system to intelligently select a very small subset of for pre-processing and then for model training and validation? Yeah, there are data splits. So you can split your data. So in the advanced training options, again, we provide options to select your split. Like you can, instead of 10%, you can do 15% split. So that is possible using one of those options. I can quickly share my screen because people are getting interested in advanced options, so it might help. So here, the models tab, clicking on train model, this is the advanced options. So batch size, you can select manually if you're aware. Like you can, if you train one model, you will get some sense of what it looks like. And I already gave you a sense of the data. So depending upon your understanding of the data in the model and the system, you will be able to select these things and play with them. So this is that test split. Like instead of 5, if you want like 2%, you can type that. But we recommend minimum 5. So that's why it defaults you to 5 if you type anything lower than that. So you can have 6 if you need. Dropout rate in the neural network, you can set to 11%. So as I said, max user length history percentile. So there are many options for you here to tweak the network, exclude time features. So depending upon the case, there might be a scenario where you don't want to take into consideration the amount of time lag that the user has between selecting or rating an item. Like in a real-time recommender system, our user might be rating an item real time. So there might be some lag in choosing the item. So sometimes that lag is important because if somebody chooses the item real quick, then that means, oh, that item must be something really cool. So that's why the person has clicked on it so fast. So that kind of lag might be useful. So some sort of thing like that is entertained using this advanced option. So there are definitely a lot of advanced options to play with if somebody has understanding of the scenario they're dealing with and the system that we offer. And then after selecting this, you can just click on train model and it will train the model using these settings. So yeah. So one more thing I would like to add. So we have a Python client library, our Python SDK. So you can use our Python SDK, but it will be like almost the same process. Instead of using the UI, now you are using the Google Colab notebook and then running those API commands, making those API calls to our system, and then trying to do the same steps that I did using the UI. So the process essentially stays the same. It's just now instead of clicking using a mouse, you're basically typing some calls and then like pressing enter to execute those calls. But yeah, I already explained how if you have a web application, you can embed using those API calls in your application and get something up and running, which is like your app being powered by an AI recommender, something like that you can accomplish. Yeah, there is a pricing info, less guessings. Yeah, I don't have the link right now on the details of that, but yeah, definitely I can share with you. Yep, I have your name recorded. I'll shoot an email to you for sure with that pricing information. Maybe your drop rate should be something between 0 to 1. So if you read the description on the dropout rate, it's on a percentage basis on our UI. So that's why you saw it like that, 11%. Okay, I think I've answered everything that is there. Yeah, hopefully it was beneficial. Hopefully you got a sense of how a real world recommendation system looks like. And you would be training your own recommender systems, I believe, hopefully in the future. So what you can do is like have your own preferences set, like create a data set of your own preferences, and then try to see what the system recommends for you. You know, using our system, you can just train a new model for your own personalization. So yeah, I think that might be a cool idea for you to try out. Using this system also, you can get a sense of what you might like. Like if there's a user that has watch history like you, then you can see what the system has generated for that user, and you might like that kind of anime as well. So that might be a cool experiment to see like how good the recommender system was when it comes to you. Okay. If there's nothing more for me, then we will take your leave. And definitely, I enjoyed my time trying to give you all the information I could for training a deep recommender system. And I appreciate your time here for sure. And I would encourage you to check out the resources that I've mentioned, our blog, our website, Abacus.AI. And if you just type /blog, it will be our blog website. And we have a YouTube channel. There are a number of past workshops that are there. This will also be available. And if you have any questions, you can definitely shoot us an email. Me and Colin would be glad to reply to your emails and solve your doubts. And stay safe. All the best. Keep learning.